Hi everyone, my name is Sylvain Lézé from the Department of Aeronautics, and this is a new episode of the podcast Turbulence at the exascale. If you're not familiar with the podcast, we are trying to gather the view of the community regarding the challenge and opportunities associated with exascale computing for turbulence research. And this podcast is part of a UK initiative called the ExCALIBUR project, which is a 5-year long project dedicated to rethinking software development to harness the power of exascale computing in the UK. The podcast is also linked with the UK Turbulence Consortium. Today, I'm very pleased we have another international guest from Sweden. It's Ricardo Vinuesa. So good morning, Ricardo.
Morning, and thank you very much for this invitation.
And so Ricardo is currently Associate Professor in the Department of Engineering Mechanics at KTH in Stockholm in Sweden. He leads the AI group and is going to talk a lot about that with a focus in fluid mechanics, engineering and sustainability. He's an expert in computational fluid dynamics, AI techniques, high performance computing and software development. So it's going to be really nice to talk to him about his research and his view about exascale computing. So I'm going to crack on with my questions, Ricardo, and for those who don't know you or don't know you very well, can you tell us a little bit more about yourself, where you are from, where you have studied, and how did you end up at KTH in Sweden?
Yeah, absolutely. I am originally from Spain, from Valencia, and that's where I did my bachelor studies in mechanical engineering. Very nice and sunny city in the Mediterranean. Then I went for a much colder weather. I went to Chicago at the Illinois Institute of Technology, and I did my master and my PhD there on mechanical and aerospace engineering. And then I started to really enjoy fluid mechanics and aeronautics. And during my period there in my PhD, I spent a month at KTH as a visiting student. And then well, I liked it, the environment. I spent a year in industry in between, but then I came for a postdoc 7.5 years ago now, and then I stayed. So I think that it's been an interesting path going towards farther north and colder weathers. But I think, yeah, it's very nice, the environment here at KTH for multidisciplinary research. So it's nice.
Excellent. Thank you very much. And I want to ask you, how did you become interested in all the stuff that you are doing now? So in high performance computing, in AI, and in turbulence?
Yeah, about HPC, it's interesting because it was during my first APS meeting in Minnesota a long time ago, I think 2009. I saw what people were doing and the type of simulations and data that I wanted to obtain, and I was really impressed. And at the time, I was actually doing more experimental work, but I became very interested in simulations, and since then I have started to work on it. And the turbulent flows during my PhD, I worked in a very nice team where I could really learn the beauty of this complex physics, but also the different approaches, experiments, theory, simulations. And more recently, machine learning. 4 or 5 years ago, during the leadership program at KTH for new faculty, I met several people working with machine learning, and we thought that we could find, the process. It was like we saw that there were areas within fluid mechanics that could benefit from these tools, and then we started to collaborate and do projects together. And I think that really there is quite some potential of this type of approaches in the context of fluid mechanics.
Great. So we are going to talk about that in a moment. So my next question, so you have been spending some time in Spain, obviously, and in the US and in Sweden. And I want to know, you already said a little bit about that, but what's the best thing about your current position at KTH? What do you really like about working there?
I mean, I really like the interaction with the students. I mean, to be able to motivate and inspire people to do not only great research, but also to contribute to the industry environment and have an impact on society. And also creating a multidisciplinary group where we have people who do simulations, machine learning, theory, experimental work. That's also very, very fulfilling. So I think those are the aspects that I enjoy the most.
Great. Before I ask you some question about your research, I have one last question. I can see that you are the Vice Director of KTH digitalization platform. So can you tell us a little bit more about this role?
Yeah, this is actually a very interesting appointment. There are 6 platforms at KTH on thematic areas that are relevant to achieve the mission of the university, and also the, let's say, to promote multidisciplinary work. And our role is to connect researchers. We have some funding for to start the projects. We don't fund the whole project, but perhaps we can fund the possibility of writing project proposals or having workshops to be able to connect the researchers with multidisciplinary work. So in that sense, we are a nexus connecting all these different people across the university doing things related to digitalization. And more concretely, I mean, I have been involved in bringing people from Vinnova, which is one of the is the innovation agency in Sweden, to talk about new calls and to kind of teach the researchers about how to apply better to be able to get these research projects. And we're working now on developing an expert group for advocacy work in the context of EU funding. So to be able to have people from different disciplines across KTH, and they can go to the EU when there are discussions about the new horizon call or new strategic areas, and that they can in a way help to provide input on this research. So I think it's a very, let's say, complete role that we do many different things, and it's also fun because of the social aspect of meeting different types of researchers as well.
Great, thank you very much. Right, let's talk about science. So before we talk in more detail, can you briefly tell us on what projects you are currently working on?
Yes, I work, I mean, on the one hand with HPC, so I still work with large-scale simulations of turbulent flows, in particular with three-dimensional wings, to start to look at wind tip vortices, their physics, their effects on the turbulence and on the aerodynamic properties of the wings. So that's one area. I also work on AI machine learning applications to turbulence, and there we have several directions: non-intrusive sensing, flow control, branch modeling, interpretable models, which is very important, not only in the context of mechanics, but in the context of AI in general. And then a third direction is a bit more related to sustainability. So I have been involved in a number of projects trying to see how AI can help sustainability and what are the synergies among applications of AI to different sustainable development goals, but also trade-offs, and what are the areas that should be more relevant in this. I have actually been I'm part of a working group, the AI for EU, which works with the European Union on the AI Act, basically, to try to get some reasonable regulation to this very important topic of AI.
Great. Well, thank you very much. So now I've a more specific question, and my first one is about data. You published recently a contribution called Data Deprivation, Data Gaps and Digital Devices, Lesson Learned from the COVID-19 Pandemics. So I think it's very timely if you could tell us a little bit more about this very important work.
Yeah, absolutely. This work was published together with Wim Naude, who is an economist, actually, from Germany. The nice thing of this type of research is that you really interact with very different profiles. And we assess really how the lack of transparency and the data usage is affecting our societies, in particular with emphasis on the differences between developed and developing countries, which, of course, all of this has been exacerbated because of COVID-19. One very important conclusion is the need for decentralized data gathering. So it has been quite controversial last year with COVID, that governments wanted to gather as much data as possible to be able to tackle the pandemic, but of course has strong implications in ethics and the personal rights of individuals. So that's one of the critical areas that we try to analyze, and also how this lack of data, relevant data, has a bigger impact in developing countries, which of course now with COVID is more problematic. So all these aspects are important, and they should be handled with, let's say, by the relevant authorities with proper plans, and keeping in mind the individual at the core. And another important aspect is the communication strategy, so that people will be able to absorb in a way these approaches to data in general. So it's a tricky topic.
I can imagine. Well, thank you very much. My next question is more related to turbulent flows, and I've seen that you've wrote a very interesting review on high fidelity simulations of complex geometry, of course, in the context of turbulence. And this might be a silly question, but what's your main conclusions after doing this review?
Yeah, this was an interesting work, because it was nice to see what is the progress in terms of, let's say, more and more complicated geometries. So one can do DNS or solve LESs in more and more complicated geometries using spectral methods. I mean, the spectral element method is quite convenient for this type of cases. And in this context, the role of AMR, of adaptiveness refinement, which is helping to build more and more complicated meshes automatically based on error estimators. But I would also say that another important conclusion of this review is the importance of having this high quality data for modeling purposes, for machine learning approaches, because now that well, we have the capability of simulating very accurately these very complicated flows, we can actually try to use that data to improve machine learning models and transmodeling, but also reduce other model development. So I think there is a nice opportunity there with the availability of new data in more and more complicated cases to have better models.
Excellent, great, thank you. Still talking about high fidelity simulation of complex geometry, of course, you need at some point to do some visualization, and I think you have been heavily involved in some software development regarding in situ visualization within Nectar 5000 using ParaView Catalyst. So can you tell us a little bit more about that? Is everything up and running within NEC 5000?
Well, this was actually a nice collaboration with the visualization group at KTH, with the group of Tino Weinkauf, and most of the software development was done by them, although we were closely collaborating in the implementation in NEC together with our students. And I mean, in this study that we recently published, I mean, we tried to do some operations in situ, so on the fly. I mean, we had the example of calculating lambda 2, so we don't have to store thousands of fields and then try to extract it a posteriori, but being able to do it on the fly, not only for the savings in storage, but also to be able to more easily assess the progress of the simulation without having to more intrusively check how the progress is going. But of course, we encounter a number of problems and challenges with balancing the loads from the various tasks, calculating the lambda 2, but also producing the images and balancing all the codes. So this, I would say that is still ongoing work. I mean, we managed to get a very nice package that allows us to fulfill this purpose, but there is still room for improvement, of course. So it's ongoing research. Great,
thank you. So we talked about data, we talked about visualization. There's another very important hot topic at the moment, that is uncertainty quantification. Sorry, and I've seen that at KTH you have a very nice tool called UQ. So can you tell us a little bit more about this UQ tool?
Yes, this is a toolbox that has been developed by a researcher in our unit, Saleh Resairaves, who is a real expert in UQ. He has really applied all these techniques based on polynomial chaos expansion, so all indices, to determine the uncertainty and sensitivity of flow simulations, which in a way it's mostly lacking in the literature to have this robust way of really looking at it. It's a completely open source library. It's available in the Journal of Open Source Software. And I would like to also mention, in the context of uncertainty quantification, other work that I have with Koji Fukagata in Japan in the context of deep learning. So we are working on probabilistic neural networks and another approach that is Gaussian stochastic weighting averaging, SWAG. And these approaches are basically aimed at getting the uncertainty of the deep learning models that we're training. So the probabilistic networks are very good at basically assessing the variability of the data that you're using for your training. And the Gaussian-based approach is more, let's say, that is very good in getting the uncertainty of the weights that you're having for the networks. So you're training several models, you're getting a Gaussian distribution, and then not only you get your prediction with a deep learning model, but you also get the uncertainty associated to that prediction, which, I mean, now that we're using deep learning for more and more things in general, having such an uncertainty bound, it becomes essential. So I think these frameworks are going to be more and more important.
Great, thank you. And so in the last few years, you have been focusing a lot on, I would say, AI and machine learning in general. And I have a simple question, which the answer is not probably going to be that simple. Do you think that machine learning is going to be, or AI is going to be a game changer in CFD? And if yes, in which areas?
Yeah, this is a very important question. Actually, I'm writing a review paper on this topic with Steve Branton from the University of Washington. So we're trying to analyze what is the potential. So far, I have the impression that there are areas within CFD where machine learning can help. So there is some work on accelerating the solution to the Poisson equation, for example. So for certain codes that would help getting better initial estimations for certain algorithms, or improving the resolution. There is some super resolution work that could be interesting. Perhaps also in terms of mesh refinement to get better error estimators. But I mean, at the moment, I think that the potential is in that direction of getting areas within the codes that can be enhanced or efficiency can be improved through machine learning. More than that, we will have to see. But I think that, and there are already examples of this, let's say, acceleration of the CFD codes thanks to machine learning. So at the moment, I think that's the most of the potential that we can get. And
this is something you mentioned at the start of this podcast. You mentioned about, a lot of people are using machine learning for turbulence modeling, and you mentioned interpretable models. So do you think that AI can have a role in this?
Yeah, that's a very good question. I mean, of course, well, of course it depends on how you define AI, which are different ways. But if we talk about deep learning versus other data-driven methods, there are data-driven methods that are inherently interpretable, as it could be genetic programming, for example, which is interpretable, maybe not so efficient or not always so accurate compared to deep learning. Deep learning are black box models from which it is difficult to really get, well, basically the underlying reasons to make a certain prediction. But there is some interesting work from Princeton aimed at trying to get the interpretability from the deep learning models. And here I would like to differentiate explainability and interpretability. Explainability of AI is a very important and very strong research area with different methods, for example, saliency methods, where you can see what part of the input is more relevant to your output. And that's important and that's helpful. But that's not giving you an interpretation result. If you're going to use an AI model to make medical decisions, well, having that explanation is not enough. And then this work from Princeton is what they're doing is that they're using genetic programming combined with inductive biases to be able to get symbolic expressions from the deep learning models. That, of course, is still at the very beginning of this area. But I think it's important because there are many applications where perhaps deep learning is the best way to go. But having that possibility of getting interpretability, my opinion, is essential for more and more applications. So it's exciting. It's an exciting area, I believe.
Great, thank you. Now I have a few questions regarding exascale computing, and my first question is very simple. And in your research group, would you say that you are ready for the transition to exascale computing? I know that KTH is going to host a brand new, or I don't know the timing, but it's going to host a brand new HPC system and with GPUs from AMD, CPUs, and so on and so on. So will you say that you're ready for the next generation of computers, or you think there's still a little bit of work to do?
Yeah, as you mentioned, exactly, there's a new machine being deployed at KTH, Dardel, which will replace the current HPC system that we have. And this machine will have a total capacity, a total power of 13.5 petaflops. So, well, still, I checked it actually, it would be around number 32 in the top 500 ranking. But the first machine, the fastest machine is already almost half an exaflop. So we are still far from there. But the interesting thing of this machine, I would say, is that it combines CPUs and GPUs. The CPU partition is over 30,000 cores, so similar to what we already have, but there is a big GPU partition already being developed. And I think the challenge, of course, is how to be able to exploit these architectures in the short term and in the long term. I mean, how can you really benefit from both, and if you can use both at the same time? And I mean, one of the research codes that we use, the spectral element code 95000, that has been used in our group for a long time. It has a GPU version developed at Argonne, and there are also some initiatives in the context of using this code in GPUs. And I believe, well, I mean, everybody is adapting to these new architectures, and we're trying to see how to compare performances, how to get the best out of these new architectures. So we are, I mean, I wouldn't say fully ready. I think one can never say that you're fully prepared, but we are doing everything we can to be able to exploit these new architectures.
Great. And a very hypothetical question: if I give you access tomorrow to an exascale computer, what would you like to study that you cannot study at the moment?
Yeah, I mean, of course, the first most intuitive answer is that, I mean, you can simulate larger cases, of course, larger and more realistic. So you can get more, in my case, of wind simulations that we have been working on for quite some time now, get into more and more complicated 3D geometries with more detail at higher Reynolds numbers and so on. But I would also argue that one interesting aspect of these new supercomputers that are going to have also a big GPU part is to be able to exploit concurrent processes. So you can do more and more things on the fly, more and more things based on in situ, and more AI-based analysis while the simulation is running. So I think that that's one exciting direction. Perhaps you want to try different control strategies as the simulation is running, and you want to do it in a very efficient way. So perhaps this type of architectures can be very suitable for this type of research, or let's say some sort of optimization task, and you want to also do that on the fly. So perhaps those very, very challenging problems can really exploit the capabilities of these new supercomputers.
Great, thank you. And I have two more questions. One is, well, both of them are actually about hardware. So obviously you are working with CPUs and GPU. And I was wondering, is for what you are doing in CFD and in machine learning, you are happy with the hardware that you have available, or you will want to see some changes? So for example, you would want more memory, you would want more compute power or more efficient network. I don't know. Do you have any ideas on this?
Yeah, I mean, of course, more computer power is always nice, but I think that one critical aspect that starts to be more and more relevant is data. And well, first of all, to be able to have more effective plans for long-term storage. That's kind of like a recurrent issue when the years start to pass and there are more and more databases. It becomes a bit challenging to be able to have a good plan for storing the data and sharing the data. And in general, I would say data handling plans, which is actually one of the things that we are pushing at the platform. I didn't mention it before, but to have, well, first of all, university-wide and later worldwide data handling plans, well, to have certain format practices, architectures, protocols for sharing. Because I mean, we all know in the context of fluid mechanics that sometimes sharing the data, because of the different formats and different nuances of every group, is not always super easy. So I think having a more standardized way of data handling will be very, very important indeed.
Great. I fully agree with you, and hopefully things will change in the data management landscape. Right, I have one last question. So we talked a little bit about exascale computers, and we are still in the very much in the petascale era for most of what we are doing. And I was wondering if you have any views on what do you think will happen in the next maybe 20, 30, 40 years. Do you think we will still be playing with CPUs and GPUs, or do you think we will have to rethink completely our software?
Yeah, I mean, I think one of the things that I'm most excited about is the possibility of, I mean, let's say in the short term with the upcoming machines, with combining CPUs and GPUs, in the sense that you can then do on-the-fly AI tasks, as I mentioned before. I think that will have a lot of promise, and that one can improve significantly the way that we do simulations and that we analyze data. Looking a bit more on the midterm, something that worries me is the electricity consumption of these large systems. Right? I mean, ICT nowadays is accounting for around 1% of the overall electricity cost, but it is expected that in 10 years, only 10 years, things continue like this, it will be 20% of the total electricity consumption, which is gigantic. And I mean, we all know that maybe practices with HPC are not always the best, and some cases are run that should not be run, perhaps, or in the context of AI, that you know, people sometimes develop models just because they can, instead of thinking a little bit what should be the most efficient model for a certain task. So I think there is a need for changing the way we think about simulations and AI models. And possibly this could also lead to some big change in the hardware itself, perhaps more efficient HPC facilities, combining different types of energy. I mean, this will be, in the context of the current climate emergency, more and more important, and something to really keep in mind, I think.
Great. I think this is a nice way of ending this podcast. So thank you very much, Ricardo, for your inputs. It was very nice talking to you about turbulence, AI, and HPC.
Thank you very much. It was a lovely conversation, and I'm very happy to be part of this podcast. And yeah, thank you.
You're welcome. Thank you very much, everyone, for listening to this podcast. As usual, you will find all the links on the Twitter from the UK Turbulence Consortium, or on the website. Just Google UK Turbulence and you will find everything you need. So thank you again, and hope to see you soon in the new episode very soon.